Welcome back to another Monash chemistry video tutorial, and this time we're going to talk a little bit about atomic orbitals and just learning how to recognize the shapes and orientations for these different atomic orbitals. We usually recognize the different atomic orbitals either by their labels, and some of the labels that you might get familiar with are things like 1s, 2p, 3d, and so on. Or you might recognize them as their shapes, which are superimposed, usually in 3 dimensions. We often sketch these on the X, Y, and Z 3-dimensional axes. If we think about an electron inside an atom, obviously as one gets further and further away from the nucleus, the probability of finding that electron gets smaller and smaller. One of the weird things about atomic orbitals is, mathematically speaking, as you get further from the nucleus, the probability never drops to 0. But it doesn't make too much sense to think of an electron being too far from the nucleus. So what we usually do to describe the location of the electron in each of these different orbitals is describe a shape which defines where the electron is likely to be found most of the time, usually about 95% of the time. And each of these orbitals has a unique shape which can be placed with respect to the X, Y, and Z axes. S orbitals are the simplest of these three. They have a spherical shape. The probability density changes uniformly moving away from the origin. As you can see, the radius of these s orbitals increases as you go from 1s to 2s to 3s and so on. P orbitals have what is often called a dumbbell shape, and these can have 3 orientations along the x, y, or z axes. And as you can see, these dumbbells are aligned along the 3 axes, and that's where they get their names from. So that px, in this case, in the figure, the 2px atomic orbital is aligned along the x-axis. That is, it's like a shish kebab with the x-axis going through the 2 lobes of the dumbbell. The py atomic orbital has the y-axis going symmetrically through the dumbbell, and the pz axis has the pz orbital has the z-axis going through the dumbbell lobes. There are 5 d orbitals, and they have the shapes and orientations that you can see here. In the case of the 3dxy atomic orbital, it gets its name from the fact that it has these nodal planes. In other words, these are planes where there is 0 probability of finding the electron, that runs along the zx and zy planes. Or you can say that the lobes are in the xy plane, and that's where this orbital gets its name from. In the 3dxz figure, you can see that the lobes exist in the xz plane, and you have nodal planes in the zy plane and also in the xy plane, and so on for dyz. The 3dx squared minus y squared orbital is slightly different to the first 3 in that the x-axis and the y-axis go symmetrically through the lobes. Finally, the 3dz squared orbital has a more odd shaped. I think of it as a dumbbell with a donut going around it, and the dumbbell is aligned along the z-axis while the donut is on the xy axis. The planes and the conical plane that you can see in that 5th example are called nodal planes. And a reminder that nodal plane is a region where you will never ever find the electron. There is a 0 probability of finding the electron in that place. Going back to the s orbitals, we can also see that there are nodal regions for the s orbitals. This is not so much in a plane, but in a spherical shape, a bit like a shell, if you like to think of it that way. Perhaps like, or the layers of an onion. Okay, in between each of those layers, where you have a non-zero probability of finding the electron, you have this shell where there is a zero probability amplitude for finding the electron. In other words, you will never find the electron there. One of the weird things about quantum chemistry is that an electron can actually go from one region through a node to the other region, but that mathematically speaking, the electron can never ever be at the spot where the node exists. There's a phenomenon called tunneling, which allows the electron to go from one non-zero probability region to a neighbouring non-zero probability region. And just revising the nodal planes that we saw with both p and d atomic orbitals. Nodal plane represents a plane about which the wave function for a particular orbital has zero probability amplitude. So in the p orbital case, we can see that there is one nodal plane, and in the d orbital we can see that there are two nodal planes.